Cool. Good morning, everybody. Welcome to one of the first sessions of the day, or of the conference altogether. My name is Ben Stock. I'm a faculty at CISPA, and I will be your session chair in this session. Do we happen to have our final speaker also? Third speaker? Perfect. I'm going to find you in a second. So in the session, it will be my job to, well, keep up with the timing, and it will be everybody in this room's job to ask the meaningful questions, because otherwise I have to. And I'm not a censorship person, so I'm very much looking forward to your expertise and your questions in this session. We're going to get right started, and the first paper is going to be on content censorship in the InterPlanetary File System. It's going to be given by Srivatsan, who's a PhD student from Stanford, and by all means, your audience.
How do the slides show up on the screen here? Okay. Okay, good morning, everyone. I'm Srivatsan. I'm a student at Stanford, and I'm talking about content censorship on IPFS, or the InterPlanetary File System. These are all my co-authors, so this is one of the papers with the 8 authors. So the InterPlanetary File System, or IPFS, is the largest decentralized peer-to-peer file system today. You can think of it as a peer-to-peer network that allows you to store and retrieve files. And it's decentralized in the sense that no single entity controls all these peers. It has about 25,000 nodes running every day and more than 1 billion files stored. Because of its decentralized nature, it's also a key storage platform for many decentralized applications and NFTs, so there's some economic value of the content stored here. And finally, also this network allows completely open participation, so anyone can join and leave the network at any point of time and start storing or serving content. I want to give you the contributions of this talk in a nutshell. So the first thing is we have a censorship attack on the IPFS, which exploits a core ingredient of IPFS, which is the Kademlia Distributed Hash Table. If you know about it, cool. If you don't know about it, I'll describe about it a bit. But the censorship attack exploits the DHT that is used for content resolution. So the idea is that the one who wants to retrieve content is unable to find where the content is stored in the network, and therefore is unable to retrieve the content. And this attack is surprisingly very low cost. We could perform it on our own content with an AWS machine that costs less than 16 cents an hour. It doesn't really require capturing or attacking any existing nodes. You just need to spawn a few nodes and do this, basically. We then have a statistical detection mechanism which detects more than 99% of the attacks. And then we have a mitigation which mitigates every occurrence of the attack. And the key thing to note is that because we can detect attacks and then mitigate them, so you don't have to incur any overhead when there is no attack. We perform experiments on the live IPFS network. So we measure the effectiveness of the attack by attacking our own content, and also the effectiveness of the detection and mitigation. And so I will show you some of those results which show how these things work in the wild. And finally, we have an implementation of the mitigation and the detection, which we are working towards integrating that into IPFS. So that's the contributions in a nutshell, and I'll get into the details now. So how does content resolution in IPFS work? So content resolution means you want to download a piece of a file from IPFS, and you want to find out where it is stored so that you can retrieve it. So for this IPFS, as I told you, it uses the Kademlia DHT. The DHT you can think of as a distributed key value store. And in this case, the keys are content identifiers, and the values are the IP address of the content provider, so the guy who stores the content. And so in Kademlia DHT, the peers who are in the network. Each of them has a pseudo-random peer ID, which is in this ID space of 256-bit strings. Now, how does Kademlia work? So if you want to provide content in IPFS, there is one of these guys who's the content provider. He has a file. The provider computes a content ID, which is nothing but the hash of the content, so it's content addressed. And first, the provider finds the k closest peers to the content ID. This means it finds the 20 peers whose peer IDs are closest to the content ID in terms of a certain distance metric, which here is like XOR of the two IDs. Right? So it finds, let's say in this example, these are the 20 closest peers. Here it's only 4 in this example. The provider sends something called the provider record to these k closest peers. The provider record is nothing but a record that contains the content ID and the provider's IP address. And these k closest peers store the provider record. When you want to download content, there's a downloader who has the same content ID. He obtains it outside, just like you would obtain a URL. Based on the content ID, the downloader does the same process to find the k closest peers and asks them who is the provider for this content ID. So these providers, these k closest peers give the downloader this provider record. So now downloader knows who is the provider, and now you can go and request the content directly from the provider. So you ask for the content, and the provider gives you the file. This makes sense? So now let's look at how the attack works, right? So the attack is going to target exactly this content resolution mechanism that I described. So notice that in this resolution process, even though it's a peer-to-peer system, the job of giving you the provider record is controlled entirely by the k closest peers to the CID, right? And so what the attacker has to do is only launch k nodes whose peer IDs lie very close to the content ID, so that now the k closest peers are controlled entirely by the adversary. So these, we call them as Sybil nodes because the adversary can just launch them. So now what happens, the provider, it sends the provider record to the k closest peers. They land on the Sybil nodes who just drop the provider record. Similarly, if the downloader requests these k closest peers for the provider record, it just doesn't respond. Notice that because the downloader already has the hash of the content, so we don't have to really worry about integrity of the data because it can always verify the hash. But censorship is the problem that we have, right? So one small detail about this, how does the adversary generate peer IDs that are close to the content ID? It turns out in IPFS, your peer ID must be a hash of your public key that's used to sign messages. So in spite of that, the adversary just needs to generate many key pairs until the hash of the public key ends up being close to the CID. And so this requires a brute force search, but it still completes in very small amount of time, like 12 seconds, basically. So it's incredibly low-cost attack. And I mentioned to you we performed this on the live IPFS network, and so we have some experiment results from that. So what I'll show you here is as we vary the number of Sybil nodes that the adversary launches, what percentage of the attempted attacks are actually effective. So the attack will be considered effective if the downloader indeed is unable to obtain the provider record, right? And so even though it's the content resolution is controlled by the 20 closest peers, if you just launch 20 Sybil peers, you can see it's only about 70% of the time the attack succeeds. We were lucky. But it doesn't matter because if you just launch 45 Sybils, then the attack is 100% successful and it doesn't increase the cost. So that's the attack and it's effective. Now I'll move on to how one can detect whether this attack is happening on a certain content ID. So the key idea for the attack is that, for the detection, sorry, is that if the attacker has launched these Sybil nodes with peer IDs that are very close to the CID, then you must have a high density of peer IDs close to this target content ID compared to the rest of the network, right? Because the adversary has concentrated its peers here. And this is the idea that was proposed originally in this reference, and we built off that. So to visualize this better, let me show you what's the distribution of the distances of the 20 closest peers from the content ID. Right? So this is essentially a histogram of the distances plotted in a log scale. So here, the blue line that you can see is sort of the ideal distribution. So if all nodes in the network were honest and their peer IDs were randomly distributed, then what would these distances look like? What's their distribution? So that's P of x. We can calculate this using, if we know how many nodes are there in the network. And so practically, you can calculate this using an estimate of the network size that IPFS already implements. On the other hand, you have an observed distribution. So if you actually do the find out the k closest peers, then what is the distribution of their distances? So this can be, if there is no attack, then it can look like these blue dots here, which matches the ideal distribution. But if there is an attack, then it can look like these red X's, which is significantly different from the ideal distribution, right? So the job is to see whether the observed distribution is close to the ideal distribution or not. And so for that, we use a standard statistical tool called KL divergence, which measures the distance between two distributions. And so if this KL divergence is high, then you say that we detect an attack. For example, the red distribution here. So this detection can be done by anybody in the network. You just need to find out the k closest peers and compare these distributions. But in particular, it's interesting for the provider to run this, because if the content provider detects an attack, now it can raise an alarm, do whatever is necessary to mitigate the attack, and so on. So how good is this detection? Notice that there is a threshold parameter, right? If the KL divergence is above a threshold, we detect an attack. If you make this threshold very low, then you will have more false detections, false positives, and the cost will be you perform some mitigation or raise alarms even when there is no attack. If you make it too high, then you miss detecting some attacks. So we need a balance, and in fact, we argue that you should favor a low false negative rate. So it's fine to have have some overhead due to mitigation, but you want to prevent all these attacks. So in the paper, we suggest a certain detection threshold, which gets about less than 1% false negatives, but about 4% false positives, right? And so if we run the detection using that chosen threshold, you detect pretty much 99% of the attacks across the number of Sybil peers that the adversary launches. So having done detection, now let me talk about how you can also mitigate the attack. So again, recall that the adversary controls the k closest peers to the content ID. One naive suggestion would be, okay, instead of sending the provider record to the 20 closest peers, I'll send it to 50, try to increase the fault tolerance. But this doesn't really work because the adversary can just launch more Sybil nodes. So it knows that you're targeting 50 nodes, it'll launch more. It just increases the cost slightly, doesn't really solve the problem. But a solution that we show works is that instead of sending the provider record to a fixed number of peers that are close to the content ID, you send it to all peers that are within a fixed distance d from the content ID. So what does this mean? The provider will now send the provider record to not just all these Sybil peers, but also to some of the honest peers. The key idea is that the honest nodes are still around. The adversary just launched more nodes, right? And how do you calculate the distance to which you want to provide? You would use the network size estimate that I mentioned earlier. And using the network size estimate, you calculate what distance d is expected to contain k honest peers. where the honest peer IDs are sort of uniformly random distributed. Right, so that is, you can find the details in the paper. It's a very simple calculation, though. The other question is, how do you find all the peers within a certain distance d? Importantly, the challenge is because the IPFS, the Kademlia DHT as implemented in IPFS, only allows these k closest peer lookups. So you can only, that's the API that the other nodes support. And so you want to be compatible with that. So in the paper, we show an algorithm of how to use multiple of these k closest peer lookups in order to find all the peers within any given distance d. And so the solution is completely compatible with existing IPFS nodes. So how effective is the mitigation? So once you implement the mitigation, 100% of the downloader's queries successfully find the provider record, and it's able to retrieve the content. So okay, it just works. There is some overhead to doing this mitigation because, as I mentioned, you need to do repeated queries of the form of get k closest peers. So there is a number of DHT lookups that grows as the number of Sybils increases. But it kind of grows slowly. It's sublinear in the number of Sybils that the adversary launches. And more importantly, because you can run the mitigation only if you detect the attack, so you can avoid like any overhead if there is no attack. Right, so with that, I'll conclude. What we show in this talk is that there's an effective mitigation strategy against a surprisingly low-cost censorship attack on IPFS. There's a detection mechanism and a mitigation mechanism that I showed you with very minimum overhead. We have an implementation of all these ingredients that is, we are working towards integrating and deploying them on IPFS. So if you want to see the implementation, you can check out the GitHub repository here. So because this is an attack, right, so we followed sort of responsible disclosure. This was work that I actually did when I was interning with Protocol Labs, who's the company that maintains the IPFS code base. So we worked closely together, and we published the vulnerability as a CVE. Finally, if you want more details, you can look at the paper using this QR code and the attack, mitigation and detection implementations have been certified by the artifact evaluators, so I encourage you to take a look at that. Yeah, we have plenty of time for questions.
All right, thank you. Is this on? Yes. All right. Anybody with a question, you just raise your hand and I get my steps in.
Yeah, hi, Lucas Drazel from UCSB, Santa Barbara. So I have two questions. The first one would be, this mitigation that you've proposed seems to be on the client side. Is there any mitigation that you as a provider can make to prevent this attack from being successful without necessarily having to modify the clients?
This is on the provider side in some sense. This is actually on the provider and the downloader side. Okay, you don't see the slides here anymore. Is it possible? Okay, so it's on both the provider and downloader side because the provider sends the provider record to all these additional peers, and so does the downloader request from all these additional peers.
Right, but without the downloader modification, it doesn't matter because it will only retrieve the k closest ones that are the Sybil nodes anyways, correct?
Yes. So you would modify both the content provider and downloader, but you don't need to modify the rest of the network.
Okay. Second question, really short one. You said that the overhead is 0 when there's no attack because you can detect the attack. What would the overhead be if you didn't do that detection step and just did the mitigation anyways?
Yeah, so the overhead is still pretty low if you run the mitigation when there is no attack. Because if there is no attack, then there are none of these red peers here. There are only the gray peers. And so even if you try to find all peers within the distance D, it pretty much requires only one DHT lookup, but sometimes it requires a little more.
Okay, thank you.
We have time for one quick question. Then please name an affiliation. Thanks.
Hi, Rob Jansen from the U.S. Naval Research Laboratory. I was expecting to see an analysis of the cost of creating Sybil's. Did you do that in the paper?
Yeah, we do. So maybe I can show you a slide there.
Because if it's cheap, then I can just continuously create Sybil's.
The cost of
Infinitely.
generating the Sybil keys, right? So this is a plot that would show you that. So roughly it takes, to generate these 45 Sybil nodes, it takes less than 12 seconds to do it. You're basically generating many, many signature key pairs until they hash to a suitable peer ID.
Do those IP addresses need to be different in the record?
They need not be different. So
then you can just
you can do them on the single machine.
create a billion Sybil's and the entire network is dead.
Yes, if you create on the order of tens of thousands of Sybil's, then you can really adversely affect the network.
Very good, thank you.
Yeah.
All right, I know there are more questions, but in the interest of time, we need to move on. Please do find the speaker afterwards, and let's thank him again.
Thank you.